Okay, next section we're going to look at is 11.4, which is tangent planes and linear approximations. I'm going to do my best to draw some of these things. They're not the easiest to draw. I would strongly suggest you work with some 3D plotters and kind of take a look at some of these graphs here. Graph the curves, graph the tangent planes, spin it around, kind of see what's going on. But I'll do my best on here. So let's do here. Start with the whole idea of in 2D. So in Calc, really Calc 1, okay, we had 2D, we had a tangent line approximates a curve at a point. So it does a good job representing what that curve, or sometimes you say how that curve behaves near that point. But as you get too far away from that point, that tangent line does not become a great approximator, okay? And you might need to find a different point to use. In Calc 3, talking 3D, just as you might expect, a tangent plane approximates a surface at a point. Okay, so that little plane kind of shows how that surface behaves close to a point. All right. So what we would do here, I'm going to try to get a little drawing. Again, here I'll do the 2D drawing too, just so you have it. So in 2 dimensions, we might have a curve. And then some point on the curve, we'll call it x naught, y naught. Why not, right? And then if we draw in our tangent line, okay, and the equation of that line, let's see here, it would be y minus y naught equals f prime of x0, right? Times x minus x naught, because it's a line. We have the point on it, x naught, y naught, and we have the slope of it, which would be f prime of x evaluated at x naught. Okay, now that purple line does a good job approximating that blue curve close to the point, but you can see the farther away we get from the point, the less accurate is it at approximating what's going on there. Okay. So now let me try to get the 2D or the 3D version. I'll try to do it on the same kind of screen here. I'm going to try to make it a little bit bigger. Okay, so we'd have Z, X. Oh, why did I put a Z there? Silly. Okay, we'd have this is Z, X, and Y. All right, and then maybe we'd have some curve or some curved surface that just kind of like goes through there, okay? Try to imagine that as like my curved surface. So we would have some point on the curve, okay, and we might call that point, here, I'm going to call it, use the same notation on each. So x naught, y naught, z naught, okay? And then, we're going to call that curve f of xy, which is z. In this case, up here, f of x was y. Okay. Let's take a look at 2 lines. Okay, so think about on this surface, the line that's tangent to the surface that's parallel to the x-axis. So you might be able to see where this is going based on what you learned in 11.4. Okay, we're going to call this tangent line 1. And then we're going to have also tangent line 2. Here, so tangent line 1, if I were to kind of draw like this blue line kind of follows the surface, and then you can see how that tangent line matches right up with that dark blue dot on the surface, and then it gets further and away from the surface as we move up or down the line. Okay, I'm going to use a different color now for our next line that would be parallel to the y-axis. Maybe this one goes like this. We're going to call that one tangent 2. And it's parallel to the y-axis, so it might kind of be right above the curve that would be like right here. Okay. There you go. That's pretty good. Okay. And I'm going to call this curve C1 and this curve C2. Okay. So again, that green one is meant to be parallel to the y-axis, moving just in the y direction. And then the purple one is meant to be parallel to the x-axis. Okay. So a couple of things here. C1 intersects the curve at y equals y0. Okay. C2 intersects at x equals x0 or x naught. Okay. T1 is a line tangent to C1 at P, and T2 is a line tangent to C2 at P also. Okay. Then the tangent plane contains T1 and T2. Okay, so that purple line and that green line, they're in the same plane. Okay, and that plane is the tangent plane. And we could draw any curve on the surface that we wanted to. It doesn't have to be parallel to the x-axis and parallel to the y-axis. Okay, but if any curve that we draw on there could have a tangent line on it, and that would lie in the tangent plane. But we really just want to focus on the ones that are in the x direction and the y direction. Okay. Now, remember the equation of a plane. Okay, so some coefficient times x minus x naught plus some coefficient times y minus y naught plus another coefficient times z minus z naught equals 0. And remember, a, b, and c give you the direction of the normal vector. X naught, y naught, z naught give you a point that's on the plane. Okay, we're going to rearrange this just a little bit. Okay, so we're going to keep c times z minus z naught on one side and get those other terms to the other side. Should be negative. Okay, and then we're going to divide by c. Okay, and now we're going to replace those. Instead of negative a over c, we're just going to call it a lowercase a. Okay, and then a lowercase b. There you go. Okay. Now, if this is the tangent plane, it intersects y equals y0. Actually, I've got these mixed up. It intersects T1 at y equals y0. Okay, so if y equals y naught, then we have z minus z naught equals a times x minus x naught, And that's the equation for T1. Okay. Now, A is the slope of T1. Okay, and that's negative A over C. So that's like your partial derivative in the x direction. Okay, think about that you're A over C. Okay, so your partial derivative in the x direction at x naught, y naught. Okay. Similarly, we could have z minus z naught equals b times y minus y naught, where b is partial y x naught, y naught. Okay, and that would be T2. So those are the equations of those two lines. T2 again is in the YZ plane. Okay, it's yeah, because it's parallel to the x-axis, how it changes in the YZ plane, and then T2 in the XY plane, or XZ plane, I'm sorry. Okay. Let's see. So what this all gets us, okay, is your big important equation of the tangent plane. Okay, so, definitely kind of look back here and think about these things and make sure they're kind of making sense in your brain. But what it all leads up to here is the equation of your tangent plane, which is z minus z naught equals the partial in x, okay, at x naught, y naught, times x minus x naught, plus your partial in y at x naught, y naught, times y minus y naught. Ta-da! This is super important. Okay, so if you're given any function, we can get a point on it to find the tangent plane, right? Because the tangent plane will change depending on which point you choose. And then we can find those partials to get the equation of the tangent plane. So let's just do an example using that, okay? Switch colors here. Okay, so an example, we have z equals 2x squared plus y squared. We want to find the equation of the tangent plane at the point 1, 1, 3. Okay, so we've got our point already. All right. If you want to graph this, probably not a bad idea. Notice that this is going to be, if z is a constant, then what we're left with here is ellipses in the xy plane. Okay, and remember ellipses are set equal to 1. Okay, and that bigger k is, the bigger the ellipse gets. Okay, and in fact, there we go. So it's always going to be twice as big in the y direction as it is in the x direction. Okay, so if we want to just do a quick little sketch of that, it's an elliptic paraboloid. In the x, you can see pretty easily that in the xz plane we'd have parabolas, and in the zy plane we'd have parabolas. In the xz plane, the parabolas are twice as fat, right? So we would have something that looks like, let's see, I said it's wider in the y direction. And z could never be negative, because x squared will always be positive and y squared will always be positive. Okay. Again, think about that xz plane. Oops, I meant to do black there. Okay, that xz plane. Okay, and then think about, I'm sorry, in your xz plane, the parabolas are twice as skinny. I mixed that up, right? And then in the yz plane, they're a little bit fatter parabolas. Okay, so make sure we can understand that. I can look at that pretty easily and see that in the xy plane I'd have ellipses, in the xz plane I'd have parabolas, in the yz plane I'd have parabolas. Okay, and you can get a little bit more specific thinking about k and how fat and wide the parabolas are. But at first glance, we can tell easily that that's something called an elliptic paraboloid. Okay, all right, so we can get to our formula. So it's always good to be able to graph these to practice that, though, before you get too far. So first of all, we want to find our partial in x, which would be 4x, our partial in y, which would be 2y. Okay, remember this is x naught, y naught, z naught. So the partial in x at 1, 1 would be 4. The partial in y at x naught, y naught would be 2. Okay, so we've got z minus z naught equals that partial in x at the point, so 4x minus x naught, plus the partial in y, so 2 times y minus y naught. Okay, so that's it. We found the equation of our tangent plane. It's always good to expand that. So z equals 4x minus 4 plus 2y minus 2 plus 3. So we would have 4x plus 2y minus 3. Okay. Now our next step would be to use that to make some approximations. All right, so we can approximate values on the curve pretty close to 113. Okay, so pretty close to an x value of 1 and a y value of 1. We can estimate some z values. Okay, so if you remember, we did this in Calc 1, right? We'd use that tangent line to make approximations near the point. So now in Calc 3, we're going to use the tangent plane to make approximations near the point. So an example here, let's see. Let's approximate, and we're going to use the same function. Okay, that z equals, with that elliptic paraboloid up there, 2x squared plus y squared. So approximate, let's say that that's f of xy, right? Okay, so approximate f of, let's do 1.1 comma 1.1. Okay, so I chose a point that's close to 1, 1 using the tangent plane. Okay, so z equals 4x plus 2y minus 3, right? That's the tangent plane at 1, 1. So f of 1.1, 1.1 will be approximately 4 times 1.1 plus 2 times 1.1 minus 3. So 4.4 minus 2.2, plus 2.2 minus 3. So 6.6 minus 3, so 3.6. Okay, so f of 1.1, 1.1 would be approximately 3.6. Okay, if you actually use the original function, which is not that hard to do, 2x squared plus y squared, f of 1.1, 1.1 is 3.62 if you plug that into your calculator. Okay, so you can see that our tangent line did a pretty good job approximating. We were only off by 200ths. Okay. Let's see. Let's move on to the next thing. A little bit more about the tangent plane, just a little bit more notation, and then we're going to get into something called a differential. So back to your tangent plane. Again, that would be z equals And let me actually go back up to how I wrote it there. Okay, we're just going to get that z naught to the other side. Okay. Okay, and we're just going to make a couple changes here. So we are going to change that tangent plane at x equals a and y equals b. Okay, so we would have z equals f of ab, okay, plus partial at ab, x minus a, plus partial yab, y minus b. Okay, and we're just doing that because you're going to see that notation. It's the same thing, right? We can call it the tangent plane. We also call it the linearization of f at AB. And so you might see it as L of xy equals all of that. Okay, we call it linearization even though it's a plane. We're still using the concept of lines there, two lines in the plane together. And we might call it the linear approximation. Or the tangent plane approximation. Of f at AB. And so what you might see for that, like this one, we're going to use an equal sign. It is the linearization. Okay, your approximation f of xy is approximately all of that. Okay, so it's just different ways that they'll word it or different symbols that they'll use, just so you're aware of it. Okay. Next thing is the whole idea of differentiability in 3D. Okay, suppose you are at AB, okay, in your xy plane, and move to a plus delta x, b plus delta y. Okay, then you're going to have some change in z, right? So let me kind of do a little, let's say we are on some curve. I'm just going to do a, okay, so let's say we are at this point here. Okay, and we move further down to another point. Maybe this point here. We don't want to plop that guy. We'll do this. Okay, so this would be a plus delta x, where delta x is the distance there. Okay, and this would be b plus delta y, where this distance between them is delta y. Okay, and then that puts us at f of a plus delta x, b plus delta y. Okay, so I'm going to kind of draw a little like cube here to kind of help you picture the 3-dimension there. Let's see. Okay, so kind of picture we're in that little back bottom corner, the green dot to start with, and then we kind of move along that curve and we end at the purple dot. Okay, so then the sides of that cube that I just, or not cube, but rectangular prism that I just drew, this side here would be delta y, this side here would be delta x, and then this side here would be delta z. Okay. So let me write something here. If z equals f of xy, can be, lost my spot in my notes here. Sorry. If z equals f of xy, so just that function, okay. Where's my pen? Okay. Then f is differentiable at AB if delta z can be expressed as delta z equals the partial at AB times however much you're moving in the x direction, okay, plus the partial y AB, delta y. And then there's going to be a little bit of an error there, right? Because this is a linear approximation. So plus E1 times delta x plus E2 times delta y. E1 and E2 are errors. E1 and E2 should go to 0 as delta x, delta y goes to 0, 0. Okay. So you kind of think about what's going on here. You're getting your change in z. Think about first moving in the x direction, okay, and that will bring you up a little bit, okay, and then so you're like in the x, and that partial brings you up a little bit. Like think about your slope in the x direction might bring you to here, okay, and then you move in the y direction, and that slope in the y direction brings you up to here. Okay, so think about this as like 2 steps. Okay, first use the differential or the partial in the x direction and how far you're moving in x direction to move up however much in z, and then take a turn in the y direction and move up. Okay, if that's true, then that means that your tangent plane approximates the graph well. Okay, there are some cases where those partials exist, but they are not good approximations. So page 644 in your book, figure 4, shows an example of where those fx and fy exist, but it's not a good approximation. Okay, and the reason is because they're not continuous. Okay, so we have what's called a sufficient condition. For a good approximation, okay? If the partials exist near your point and are continuous at your point, then f is differentiable at AB. And in other words, your tangent plane is a good approximator. Okay, so again, a lot of talk there, but what we're really getting at here is an example. If we had f of xy equals xe to the xy, and we want to know if it's a good approximation at 1, 0. If that tangent plane at 1, 0 would be a good approximator. Okay. In other words, they want you to use linearization, okay, your tangent plane approximation, to approximate f of 1.1, negative 0.1. Okay, so we're pretty close to 1, 0. Okay, so we're going to check that sufficient condition first of all to see if it will be a good approximation. So our partial in x, let's see, we would have first times derivative of the second plus the second times the derivative of the first, which would be, so we'll just simplify it a little bit. Okay, that's continuous at 1, 0 and everywhere. Okay, so there's no discontinuities in that function. Nothing would make it undefined. Your partial for y would be xy e to the xy. Oops, I missed something, didn't I? Yes, I did. I'm gonna rethink. If we're taking the partial at y, then x is a constant. Okay, so we would have x times x e to the xy, or x squared e to the xy. Okay, and again, that's a function, it's continuous everywhere. There are no discontinuities there. Okay, so we're meeting that condition. They both exist at 1, 0, and they're continuous at 1, 0 because they're continuous everywhere. So we can do that approximation. Okay, the partial in the x direction at 1, 0 would be e to the 0 times 0 plus 1, so it would be 1. Partial in y at 1, 0 would be 1 e to the 0, which is also 1. Okay, so our linearization at 1, 1 will be f of 1, 1 plus the partial at 1, 1 times x minus 1 plus the partial at 1, 1 times y minus 1. Okay, we didn't figure out, or no, I'm sorry, it's at 1, 0. Yeah, let me change those the second ones to zeros. I don't know why I did that. That would be, get those fixed for you. There we go. Okay. Oop, missed that 0. Okay, so f of 1, 0 we also need, so that would be 1 e to the 0, which is 1. Okay, so your linearization at 1, 0 is 1 plus 1 times x minus 1 plus 1 times y. Okay, in other words, it would be 1 plus x minus 1 plus y, or it's just going to be x plus y, right? Or 1 plus x, no, x plus y. Okay, so your function at, where did we want to do it here? We wanted to do it at 1.1, negative 0.1 will be approximately 1.1 plus 0.1, which is 1. Okay, so first we came up with our linearization at 1, 0, and then we use it to estimate a value close to 1, 0. Okay, in reality, if you go back to that original function, that x times e to the xy, plug it into a calculator, the actual value, 0.98542. So we are pretty close with that. Okay. All right, I think I'm going to just keep going with this video rather than making separate ones because it's not getting too glitchy on me. So the next thing that we're going to talk about is differentiables. Or sorry, I keep saying that, differentials. Differentials. Okay, and it's going to be easier here if we start with what a differential is in 2D. So come back to our little drawing here where we've got a curve. You know what? I think I spoke too soon. It's getting a little glitchy on me. So I'm going to stop this video and then I'll do a new video that explains differentials. Okay? So let me stop that.